Hello, and welcome back to Sleepy Tin Foil Hat. Tonight, we're going to drift into one of those strange corners of science where curiosity, secrecy, and imagination quietly overlap. A place where official research meets whispers of experiments that never quite made it into textbooks. A place where gravity itself, the invisible force that keeps your feet on the ground, may not be quite as simple as we once believed. For most of human history, gravity was something mysterious yet unquestioned. Apples fell from trees. Oceans stayed wrapped around the planet. The moon circled Earth in a slow, patient rhythm. It was simply the rule of the universe. But over the last century, scientists began to look at gravity a little differently. Instead of accepting it as an unchangeable force, they started asking something unusual. What if gravity could be altered? What if it could be reduced, redirected, or even temporarily turned off? And perhaps even more curious, what if governments and space agencies quietly explored those ideas long ago? Tonight we'll wander through the quiet edges of that question. Not in a frantic or sensational way, but slowly, gently. The way a late-night documentary might guide you through the deeper mysteries of physics. We'll talk about strange experiments from NASA laboratories, unusual patents, mysterious propulsion theories, and the scientists who wondered whether gravity might behave very differently under the right conditions. Some of these ideas were tested, some were abandoned, and some remain oddly difficult to explain. But before we float too far into the story, take a moment to get comfortable. If you enjoy these slow explorations of science, hidden research, and curious mysteries, consider subscribing to Sleepy Tin Foil Hat. And if you feel like it, leave a comment telling me where in the world you're listening from tonight. I always enjoy seeing how far these quiet conversations travel across the planet. For now though, there's nothing you need to do. Let your shoulders relax. Let the room grow quieter around you. And as your breathing slows, we'll begin gently exploring one of the most fascinating questions NASA engineers ever asked themselves. What if gravity wasn't as permanent as it seems? To understand where the idea of anti-gravity began, we have to travel back to the early days of the space age. The 1950s and 1960s were a strange and exciting time. Rockets were new, satellites were just beginning to appear in orbit, and humanity had suddenly realized something astonishing. Space was reachable. But there was a problem. Gravity. Every rocket launch required enormous energy just to escape Earth's grip. Engineers calculated that lifting a single kilogram into orbit required massive amounts of fuel. Entire rockets were designed around that single problem: overcoming gravity. And so some scientists began asking a quiet question. What if there was another way? Not stronger rockets, not bigger engines, but a method that somehow worked with gravity instead of against it. One of the earliest scientists to seriously explore this possibility was a physicist named Thomas Townsend Brown. Brown became fascinated with electricity and gravity while experimenting with high-voltage capacitors in the 1920s. During his experiments, he noticed something strange. When he applied extremely high voltage to certain capacitor designs, the devices appeared to move slightly, almost as if a tiny force was pushing them forward. Brown believed he had discovered something extraordinary. He thought electricity might interact with gravity. If true, it meant that under the right electrical conditions, gravity itself might be influenced or even reduced. He called the effect electrogravitics. For decades, Brown demonstrated devices that appeared to drift or glide when exposed to strong electric fields. Small triangular craft, sometimes called lifters, would rise gently into the air with no propellers, no engines, and no visible means of propulsion. Just electricity. To many scientists, the explanation seemed simpler, and they believed the motion was caused by ionized air, a phenomenon known as ionic wind. But the experiments were intriguing enough that, during the Cold War, several aerospace companies quietly took interest. In the 1950s, major defense contractors such as Lockheed, Glenn Martin, and Convair reportedly studied electrogravitics. Some engineers speculated that future aircraft might glide silently, using electric fields instead of jet engines. Imagine airplanes with no propellers, no roaring turbines, simply floating forward through subtle interactions between electricity and gravity. It sounded almost impossible. And yet, research continued. Even NASA's predecessor organizations quietly investigated unusual propulsion ideas during those early space race years. At the time, the United States and the Soviet Union were both searching for any advantage that could make space travel easier. If gravity could somehow be reduced, even slightly, it would change everything. Rockets could become smaller, spacecraft could travel farther, and leaving Earth might require far less energy. But gravity has always been stubborn. Unlike electricity or magnetism, gravity is incredibly weak. In fact, compared to other forces of nature, gravity is almost unimaginably tiny. A simple refrigerator magnet can easily overpower the entire gravitational pull of Earth, at least for a small paperclip. This strange imbalance has puzzled physicists for generations. Why is gravity so weak? Some researchers believe the answer may lie in hidden dimensions of space, ideas that modern physics sometimes refers to as extra dimensions or brane worlds. According to certain theoretical models, gravity might appear weak because part of it is leaking into other dimensions beyond our perception. If that were true, it raises a fascinating possibility. What if gravity could be manipulated by interacting with those hidden dimensions? NASA researchers have occasionally explored these ideas in highly theoretical studies. In fact, in the late 1990s and early 2000s, NASA even funded a small program called the Breakthrough Propulsion Physics Program. The goal was simple: investigate whether completely new propulsion methods might exist, even if they seemed impossible at first. The program studied concepts like warp drives, space-time manipulation, and gravity control. Most of the work was theoretical. No anti-gravity engines suddenly appeared. But the fact that NASA studied these ideas at all is quietly fascinating, because it tells us something important. Scientists are willing to explore even the strangest possibilities, if the physics might allow it. One particularly curious line of research involves something called superconductors. Superconductors are materials that, when cooled to extremely low temperatures, allow electricity to flow with zero resistance. In the 1990s, a Russian scientist named Eugene Podkletnov claimed to observe something very strange while experimenting with spinning superconductors. He reported that objects placed above a rapidly rotating superconducting disk seemed to lose a small amount of weight. Only a tiny amount, about 1 or 2%. But if the effect were real, it suggested something extraordinary, a possible interaction between superconductivity and gravity. The claim caused a brief storm of interest across physics communities. Laboratories attempted to reproduce the experiment. Some reported strange measurements. Others found nothing at all. The results were never fully confirmed, and the idea faded quietly into the background of scientific discussion. Still, the experiment remains one of those curious moments where gravity briefly seemed flexible. NASA scientists even examined the claim during the early years of the Breakthrough Propulsion Program. Not because they expected anti-gravity machines tomorrow, but because even a tiny gravitational effect could reveal something new about the nature of space itself. And that brings us to one of the deeper questions behind all of these experiments. What is gravity, really? Isaac Newton described gravity as a force pulling objects together, but Albert Einstein later proposed something very different. According to Einstein, gravity isn't a force at all. It's the curvature of space-time. Massive objects like Earth bend the fabric of space around them. objects moving nearby simply follow those curves. In a sense, planets aren't pulled by gravity. They're sliding along invisible slopes in the geometry of space itself. If that's true, then controlling gravity would mean controlling space-time. And that idea, as strange as it sounds, is something modern physics continues to explore. Not with secret anti-gravity ships hidden in hangars, but through careful experiments, quiet calculations, and patient research. Because the universe still holds many mysteries, and gravity, the force that seems so ordinary every time we drop a spoon or watch rainfall, may still be hiding deeper secrets beneath its familiar pull. For now, though, let those ideas drift gently through your thoughts. No need to solve them tonight. Just imagine the possibility that somewhere, in a quiet laboratory, scientists are still asking the same question. Could gravity, someday, be understood well enough to guide us through space in ways we've never imagined? And if that day ever comes, the journey beyond Earth might become much calmer, quieter, and perhaps even a little easier. For tonight, though, we'll keep drifting slowly through the strange and relaxing history of NASA's most curious propulsion ideas, because some of the most unusual anti-gravity concepts didn't involve electricity or superconductors at all. They involve something even stranger, the idea that spinning objects might slightly twist the fabric of space itself. And that story begins with a physicist who noticed something unusual about rotating masses. But we'll ease into that part of the mystery slowly. For now, let the quiet settle in. As we continue drifting through these quiet corners of space research, let's move gently toward another idea that once fascinated physicists and engineers alike. It's an idea that sounds subtle at first, almost too simple to matter, yet it touches on one of the deepest predictions of Einstein's theory of relativity. The idea is this: when something massive begins to spin, it may slightly twist the fabric of space itself. Now imagine that thought for a moment. Space, according to Einstein, is not an empty stage where events happen. Instead, space and time form a flexible fabric called space-time. Massive objects bend that fabric, creating the effect we call gravity. But when those objects rotate, something even stranger can occur. The spinning mass drags space-time along with it. Physicists call this effect frame dragging. You can picture it like a heavy bowling ball placed on a stretched rubber sheet. If the ball simply sits there, it creates a deep curve. But if you spin the ball, the surface around it begins to twist slightly, like syrup swirling around a spoon. Earth itself actually does this. Our planet's rotation causes a tiny frame-dragging effect in the space surrounding it. Satellites orbiting Earth feel this twist, though the effect is extremely small. So small, in fact, that it took decades for scientists to measure it precisely. One of the most famous experiments designed to detect this phenomenon was a NASA mission called Gravity Probe B. The spacecraft launched in 2004, carrying 4 incredibly perfect gyroscopes. These gyroscopes were polished spheres so smooth that if Earth were made with the same precision, its tallest mountains would only be a few centimeters high. Their purpose was simple in concept, though incredibly delicate in practice. If Earth truly drags space-time as it spins, the gyroscopes should slowly tilt over time in a very specific direction. After years of data collection and analysis, the results confirmed Einstein's prediction. Space itself was indeed twisting, ever so slightly, around our rotating planet. Now you might be wondering what this has to do with anti-gravity. Well, during the early space age, some physicists wondered something bold. If a rotating planet can drag space-time, what happens when extremely fast spinning objects are created in laboratories? Could artificial rotation produce measurable gravitational effects? The idea led to decades of theoretical exploration. Some researchers suggested that extremely dense rotating masses might generate detectable distortions in space-time. Others imagined rings of rapidly spinning matter that could produce unusual gravitational fields. Most of these concepts remained firmly in the realm of theory. The problem was scale. Planets are enormous. Their mass and momentum are what create measurable frame-dragging effects. Replicating anything remotely similar in a laboratory would require energy and materials far beyond our current capabilities. But that didn't stop scientists from wondering whether smaller, subtler effects might exist. And occasionally, experiments appeared that hinted at something unusual. In the late 20th century, several laboratories began exploring something called gravitomagnetism. This concept comes directly from Einstein's equations. Just as moving electric charges produce magnetic fields, moving masses might produce something similar, a gravitational version of magnetism. In theory, large rotating masses could create tiny gravitomagnetic fields. If true, it meant gravity might behave more dynamically than we usually imagine. Instead of a simple downward pull, gravity might include swirling patterns created by motion. NASA researchers studying advanced propulsion concepts briefly considered whether such effects could ever be engineered. Imagine, for instance, a spacecraft with large rotating superconducting rings. If those rings could somehow amplify gravitomagnetic interactions, perhaps they could produce tiny distortions in space-time around the vehicle. Not enough to turn gravity off entirely, but maybe enough to reduce inertial mass slightly. Even a tiny reduction could revolutionize propulsion. A spacecraft that effectively weighed less would require far less energy to accelerate. Of course, no such technology has ever been demonstrated. But the mathematics behind gravitomagnetism remains part of accepted physics, which means the question still lingers quietly in the background. Could extreme engineering someday interact with gravity in ways we barely understand today? Another curious idea explored by theoretical physicists involves something called vacuum energy. At first glance, the vacuum of space seems completely empty, a vast darkness with nothing in it at all. But quantum physics tells a very different story. According to quantum field theory, even empty space is buzzing with activity. Tiny particle pairs constantly appear and disappear in fleeting moments called quantum fluctuations. These fluctuations create a faint background energy throughout the universe. Physicists sometimes call it zero-point energy. Most of the time, this energy remains hidden beneath the surface of observable physics. But some researchers have wondered whether manipulating vacuum energy could influence gravity itself. One famous example of this idea is the Casimir effect. When two perfectly flat metal plates are placed extremely close together in a vacuum, something strange happens. Quantum fluctuations outside the plates are slightly stronger than those between them. This creates a tiny pressure difference that gently pushes the plates together. The force is incredibly small, but it has been measured in laboratories. Some theorists have speculated that manipulating vacuum energy on larger scales could potentially interact with gravity. NASA's Breakthrough Propulsion program briefly examined such possibilities. They weren't building anti-gravity engines, of course, but they were exploring whether exotic physics might someday open doors we haven't yet imagined. Another quiet thread in this story involves unusual patents that appeared over the years. Occasionally, inventors have filed designs claiming gravity manipulation or inertial reduction devices. One of the more widely discussed patents came from an engineer working for the US Navy named Salvatore Pais. His proposed craft described a high-energy electromagnetic system that might theoretically interact with quantum vacuum fields. The patent described something called an inertial mass reduction device. In simple terms, the idea suggested that certain electromagnetic fields could alter the inertia of a craft, effectively making it easier to accelerate and maneuver. The patent sparked plenty of debate. Many physicists remained skeptical. The proposed mechanisms would require energy levels far beyond anything currently achievable. But the existence of such ideas within official patent systems showed that curiosity about gravity manipulation had never fully disappeared. Even today, advanced physics continues to explore the nature of gravity with new instruments and theories. One of the biggest mysteries involves something called dark energy. When astronomers measured the expansion of the universe, they discovered something astonishing. The expansion is accelerating. Something unseen appears to be pushing galaxies apart. Whatever this force is, it seems to act almost like anti-gravity on the largest scales of the cosmos. Dark energy now appears to make up nearly 70% of the entire universe. Yet scientists still don't fully understand what it is. Some theories suggest it could be related to vacuum energy. Others propose entirely new fields of physics that we have yet to detect directly. And while dark energy operates on cosmic scales far beyond human technology, it reminds us of something important. Gravity may still hold secrets. For thousands of years, gravity seemed like the simplest force in nature. Objects fall, planets orbit, the moon pulls on the tides. But modern physics has revealed that gravity connects to the deepest structure of reality itself. Space, time, energy, and motion are all woven together. And when scientists explore gravity, they are really exploring the shape of the universe. That's part of what makes these quiet NASA studies so fascinating. Not because secret anti-gravity machines are hiding in underground hangars, but because the question itself is so profound. Could gravity ever be controlled, even slightly? For now, the answer remains uncertain. But every satellite orbit, every physics experiment, and every deep space mission slowly adds pieces to the puzzle. And sometimes, when the night is quiet and the stars are out, it's comforting to imagine the possibilities waiting out there. Perhaps centuries from now, travelers will cross the solar system using technologies that seem impossible today. Maybe gravity will be something future engineers shape and guide, the way we now guide electricity through wires. Or maybe gravity will remain a gentle, mysterious force that reminds us just how much we still have to learn. For tonight, though, we'll keep drifting gently through these ideas, because there is another strange chapter in the story of gravity research, one that involves unusual rotating devices, strange laboratory measurements, and scientists who briefly wondered whether gravity itself might respond to spinning matter in unexpected ways. As we keep drifting through these quiet corners of gravity research, let's move into one of the more curious episodes that quietly appeared in physics journals during the late 20th century. It's a story that doesn't begin with spacecraft or large government programs, but with laboratory equipment that looked almost ordinary. Simple devices, spinning disks, sensitive instruments, and a handful of scientists who began to notice something that didn't quite behave the way they expected. Now, when physicists test gravity in a laboratory, the changes they measure are incredibly small. Gravity is already the weakest of the known fundamental forces, so any experiment looking for tiny variations requires extremely careful conditions. Temperature must remain stable, air movement must be minimized, vibrations must be reduced as much as possible. Even footsteps in a hallway can sometimes affect the most delicate instruments. Because of this, many gravity experiments are performed deep underground or in specialized laboratories designed to isolate the equipment from environmental noise. In the 1990s, a few experimental physicists began exploring the behavior of rotating masses in extremely controlled environments. The idea was not anti-gravity exactly, but rather something slightly more subtle. They wanted to see whether rapidly spinning objects could create tiny gravitational anomalies, not because physics predicted dramatic effects, but because Einstein's equations allowed for extremely faint interactions related to motion and rotation. One group of researchers began studying rotating cryogenic systems. When these were devices cooled to extremely low temperatures, where materials behave differently than they do under normal conditions. At these temperatures, certain metals become superconductors, allowing electric current to move with zero resistance. Superconductors already produce fascinating effects in magnetism. They can levitate magnets above their surface using what's known as the Meissner effect. where magnetic fields are expelled from the material. But gravity and magnetism are very different forces, or at least they appear to be. Still, some scientists wondered whether superconductors interacting with strong electromagnetic fields might reveal deeper relationships between the forces of nature. So the experiments began. Large disks of superconducting material were suspended inside vacuum chambers. They were cooled to extremely low temperatures using liquid helium or liquid nitrogen. Then they were spun at very high speeds. Sensors above and around the disks measured tiny forces and weight variations in nearby objects. Most of the time, nothing unusual happened. Measurements behaved exactly as expected. Gravity remained constant, but occasionally, small irregular readings appeared. Some researchers reported brief fluctuations in weight measurements near spinning superconductors. The effects were extremely small and difficult to reproduce consistently. In most cases, they could be explained by vibrations, magnetic interference, or measurement noise. Yet the idea lingered long enough to attract curiosity. If rotation, superconductivity, and electromagnetic fields could interact with gravity even slightly, it would open an entirely new branch of physics. One experiment that often comes up in discussions of these ideas is associated with the Italian physicist Giovanni Modenese. Modenese explored theoretical models, suggesting that certain superconducting conditions might influence gravitational interactions at a quantum level. His work didn't claim that anti-gravity devices existed. Instead, it suggested that the relationship between quantum mechanics and gravity might be far more complex than currently understood. And that complexity is one of the biggest unsolved puzzles in modern science. You see, physics currently rests on two incredibly successful theories. The first is general relativity, Einstein's theory describing gravity and the curvature of space-time. And the second is quantum mechanics, which describes the strange and unpredictable behavior of particles at very small scales. Both theories are extraordinarily accurate. Both have passed countless experimental tests, but they don't fully agree with each other. General relativity describes the universe on large scales: planets, stars, galaxies. Quantum mechanics describes the microscopic world: atoms, electrons, and subatomic particles. And yet, when physicists try to combine the two theories into a single framework, the equations begin to break down. Gravity refuses to fit neatly into the quantum picture, which means there may still be pieces missing from our understanding. Some researchers believe that gravity might eventually be explained through particles called gravitons, hypothetical carriers of the gravitational force. Others think gravity might emerge from deeper geometric structures of space-time. And still others explore ideas involving hidden dimensions, vibrating strings, or quantum fields that exist beyond our current measurements. NASA's interest in advanced propulsion often touches these deeper questions, not because they expect gravity drives tomorrow, but because understanding gravity better could change everything about how we move through space. Right now, spacecraft travel using chemical rockets, ion thrusters, or gravitational assists. Gravity assists are particularly elegant. When a spacecraft passes close to a planet, it can borrow a little bit of that planet's orbital energy. The spacecraft swings around the planet like a slingshot and leaves with greater speed. This technique has allowed probes like Voyager, Cassini, and New Horizons to travel vast distances using surprisingly little fuel. But gravity assists still rely on gravity behaving normally. The dream of many propulsion theorists is something more direct, a way to control gravitational fields themselves. If gravity could be shaped or redirected, even slightly, spacecraft might accelerate smoothly without enormous rockets. Instead of blasting into orbit with explosive force, vehicles might simply glide upward, gently detaching from Earth's gravitational slope. It's a beautiful idea, and one that has inspired countless speculative designs over the decades. Some concepts involve rotating rings that generate artificial gravity gradients. Others imagine electromagnetic fields interacting with space-time curvature. And still others explore the possibility that inertia and gravity might be linked more closely than we currently realize. In fact, one of the oldest philosophical questions in physics touches directly on this idea. It's known as Mach's principle. The principle suggests that inertia, the resistance objects have to acceleration, may arise from the gravitational influence of all matter in the universe. In other words, when you push on an object and feel resistance, that resistance might somehow be connected to the gravitational pull of distant stars and galaxies. Einstein himself was fascinated by this concept. If inertia truly depends on the structure of the universe, then manipulating local gravitational conditions might alter inertial properties as well. Some speculative propulsion ideas attempt to explore exactly that possibility. NASA researchers studying advanced propulsion theories occasionally discuss something called inertial mass modification. If the inertial mass of a spacecraft could be reduced, even slightly, it would require less energy to accelerate. The craft would behave as if it were lighter, without actually losing mass. So far, this remains purely theoretical, but it illustrates just how deeply scientists are willing to think when exploring the future of space travel. Because the stakes are enormous, interstellar travel, for instance, remains far beyond our current technology. Even our fastest spacecraft would take tens of thousands of years to reach the nearest star. Yet if gravity or inertia could be manipulated, travel times might shrink dramatically. Distances that once seemed impossible could become reachable. Of course, these ideas remain distant possibilities, and for now, gravity continues to behave exactly as it always has, quietly pulling oceans toward the moon, holding planets in their orbits, keeping our feet comfortably on the ground. But the story of science is full of moments where forces once considered permanent turned out to be more flexible than expected. Electricity was once mysterious lightning. Magnetism was once strange, invisible attraction between stones. Even flight seemed impossible until the right understanding of aerodynamics emerged. Gravity may still be waiting for its next great breakthrough, or perhaps it will remain exactly as Einstein described it, a beautiful curvature in the geometry of space. Either way, exploring the question brings us closer to understanding the universe itself. And sometimes, that quiet exploration is the most relaxing part of the journey. For now, let those ideas drift slowly through your mind. Imagine scientists in quiet laboratories, instruments humming softly, watching tiny measurements appear on glowing screens. Most of the readings ordinary, but every now and then, something slightly unexpected. A number that doesn't quite match the prediction. A tiny mystery waiting patiently to be understood. And those mysteries are often where the next discoveries begin. As we continue drifting through these quiet and curious chapters of gravity research, let's move gently toward a mystery that puzzled scientists for many years. Not in a laboratory on Earth, but far out in the silent depths of space. This story begins with two spacecraft launched by NASA in the early 1970s. They were called Pioneer 10 and Pioneer 11. At the time, these spacecraft represented some of the most ambitious robotic explorers humanity had ever sent beyond Earth. Their mission was simple in concept, though incredibly challenging in execution. Travel to the outer solar system, study Jupiter, and for Pioneer 11, Saturn as well. Then continue onward, deeper into space than any spacecraft had gone before. The Pioneers were relatively small compared to modern probes, but they were designed with extraordinary precision. Their trajectories were carefully calculated so that scientists could predict their motion through the solar system with remarkable accuracy. After completing their planetary encounters, the probes continued drifting outward, slowly leaving the gravitational influence of the sun behind. For decades, they transmitted faint radio signals back to Earth. Each signal carried tiny shifts in frequency that allowed scientists to track the spacecraft's velocity and position with astonishing precision. And that's when something strange began to appear. As the years passed, researchers noticed that both Pioneer spacecraft seemed to be slowing down, ever so slightly, more than expected. The difference was incredibly small, only about 8.74 times 10 to the power of minus 10 meters per second squared. That number is almost unimaginably tiny, but over long distances and long periods of time, it was measurable. The spacecraft appeared to be experiencing a faint extra pull toward the sun, not strong enough to dramatically alter their paths, but just enough to make scientists curious. The effect became known as the Pioneer anomaly. At first, researchers considered the usual explanations. Perhaps gravitational influences from distant planets had been miscalculated. Maybe tiny leaks in the spacecraft's propulsion system were creating a gentle push. Or perhaps solar radiation pressure, the tiny force exerted by sunlight, was slightly stronger than expected. But none of these explanations immediately solved the mystery. And for a while, something intriguing began to circulate through the physics community. What if the anomaly represented new physics? Some scientists briefly wondered whether gravity itself might behave slightly differently at extreme distances from the sun. Others speculated about modifications to Newtonian gravity or Einstein's equations on large scales. The idea wasn't completely unreasonable. After all, astronomy had already discovered several phenomena that challenged our understanding of gravity, including dark matter and dark energy. So researchers began to investigate the Pioneer anomaly carefully. Teams around the world analyzed decades of spacecraft data. Old telemetry records were retrieved from archives. Detailed computer models simulated every possible force acting on the probes. And slowly, the mystery began to unravel. The answer, when it finally emerged, turned out to be both elegant and surprisingly simple. It involved heat. You see, the Pioneer spacecraft were powered by radioisotope thermoelectric generators, often called RTGs. These generators produce electricity by converting the heat released from slowly decaying radioactive material. That heat doesn't disappear. Most of it radiates into space as infrared energy. And when heat radiates unevenly from a spacecraft, it can create a very small push, almost like a faint photon-powered thruster. Over long periods of time, this tiny thermal recoil force was enough to slightly alter the spacecraft's motion. Once scientists modeled the heat patterns carefully, the anomaly disappeared. The Pioneer probes weren't revealing new physics after all. They were simply being nudged very gently by their own warmth. Now, at first glance, this might seem like a slightly disappointing ending. A mysterious anomaly, explained by ordinary heat radiation. But in reality, it was a beautiful example of how precise modern science has become. Imagine detecting the motion of a spacecraft billions of kilometers away, and realizing that the warmth from its internal systems can change its velocity by less than a billionth of a meter per second each second. It's an astonishing level of sensitivity, and it reminds us that when scientists search for new physics, they must first account for every possible ordinary explanation. Still, the Pioneer anomaly served an important purpose. For a time, it encouraged researchers to examine gravity more carefully than ever before. And that careful examination has led to new experiments designed to test gravity with incredible precision. One example is the ongoing effort to measure something called the equivalence principle. The equivalence principle is one of the cornerstones of Einstein's theory of relativity. It states that gravitational mass and inertial mass are exactly the same. In simple terms, this means that all objects fall at the same rate in a gravitational field. regardless of their composition. A feather and a hammer fall differently on Earth only because of air resistance. In a vacuum, they fall together perfectly. Astronauts demonstrated this beautifully during the Apollo 15 mission, when a hammer and feather were dropped simultaneously on the moon. They hit the surface at exactly the same time, but scientists still test this principle constantly. If even the tiniest difference were ever discovered between gravitational mass and inertial mass, it would suggest new physics beyond Einstein's theory. To test this idea, space agencies have launched incredibly sensitive experiments. One such mission, called Microscope, was developed by the French Space Agency and launched in 2016. It placed extremely precise instruments into orbit to compare how different materials respond to gravity. After years of data collection, the results confirmed the equivalence principle with astonishing accuracy. So far, gravity behaves exactly as Einstein predicted, but the search continues, because scientists know that our understanding of the universe is still incomplete. Dark matter appears to influence the motion of galaxies. Dark energy seems to accelerate the expansion of the universe, and gravity, the force that governs both of these mysteries, remains the least understood of the fundamental interactions. NASA continues to study gravity through missions that explore planets, moons, and asteroids. By tracking spacecraft trajectories with extreme precision, scientists can map gravitational fields across the solar system. For example, missions like Juno orbiting Jupiter measure tiny variations in gravity that reveal what lies beneath the planet's swirling clouds. Other missions map the gravitational fields of asteroids to understand their internal structure. Every measurement adds another piece to the puzzle. And while none of these missions have discovered anti-gravity technology, they are steadily expanding our knowledge of how gravity truly works. As sometimes progress in science comes not from dramatic breakthroughs, but from patient observation, careful measurements, and the willingness to question even the most familiar forces in nature. Gravity may seem simple when we feel it pulling us gently toward the ground, but on cosmic scales, it shapes galaxies, bends light around stars, and governs the motion of the universe itself. And perhaps somewhere within its quiet equations, there are still surprises waiting. For now, though, the Pioneer probes continue their silent journey outward. Long after their instruments stopped transmitting, they kept drifting into the darkness between stars. Each one carries a small plaque, a message from Earth, and a quiet reminder of humanity's curiosity. They are still out there, moving slowly through interstellar space, being guided only by gravity and the momentum of a journey that began decades ago. And as we rest here tonight, thinking about these distant explorers, it's comforting to imagine them gliding quietly through the vast calm of space. No engines firing, no noise, just silent motion through the fabric of the universe. Now, as we continue our slow drift through these quiet and curious ideas, we arrive at one of the most fascinating concepts ever discussed in theoretical physics. It's a concept that sounds almost like something pulled straight from science fiction. Yet it was proposed by a serious physicist and even studied, in small ways, by NASA researchers. The idea is known as the warp drive. At first glance, the concept seems almost impossible. After all, according to Einstein's theory of relativity, nothing can travel faster than the speed of light. This limit appears to be one of the fundamental rules of the universe. Light travels at about 300,000 kilometers per second. Even our fastest spacecraft move at only a tiny fraction of that speed. The vast distances between stars make interstellar travel incredibly difficult using conventional propulsion. For example, the nearest star system, Alpha Centauri, is more than 4 light-years away. With our current technology, reaching it would take tens of thousands of years. And yet, in 1994, a Mexican physicist named Miguel Alcubierre proposed something remarkable. He suggested that while objects cannot move faster than light through space, space itself is not limited by that rule. Space can expand. Space can contract. In fact, the universe itself has been expanding since the Big Bang. Galaxies are being carried apart as the fabric of space stretches between them. This led Alcubierre to ask a bold question. What if a spacecraft didn't move through space at all? What if it moved with space? His idea was elegant in its simplicity. Imagine a spacecraft sitting inside a bubble of space-time. If space in front of the bubble could be compressed, and space behind the bubble could expand, the bubble itself would move forward. The spacecraft inside would remain locally stationary, but the space around it would carry it across vast distances. In theory, the bubble could move faster than light relative to distant observers, without violating Einstein's rules. Inside the bubble, the spacecraft wouldn't feel extreme acceleration. Passengers could experience a calm, smooth journey. It's a beautiful idea, but there's a problem. Actually, several problems. The biggest issue is energy. And early calculations suggested that creating such a warp bubble would require enormous amounts of exotic matter, a form of matter with negative energy density. Negative energy is a strange concept, but it appears in certain quantum phenomena. However, the quantities required for a warp drive would be immense. Some estimates suggested more energy than the mass of entire planets. Later refinements reduced the requirements somewhat, but the numbers are still far beyond anything humanity can currently produce. Still, the idea captured the imagination of physicists and engineers alike, not because they expected warp drives anytime soon, but because the equations themselves were valid solutions within Einstein's theory. And whenever physics allows a strange possibility, scientists become curious. And NASA's breakthrough propulsion physics program, which ran during the late 1990s and early 2000s, briefly explored the theoretical aspects of warp drive concepts. Researchers didn't build warp engines, of course, but they studied the mathematics carefully. Could exotic energy exist in usable quantities? Could space-time distortions be measured in laboratories? Were there subtle ways to test the physics behind these ideas? Later, a small research group at NASA's Johnson Space Center, sometimes referred to as the Eagleworks Laboratory, continued examining theoretical warp concepts. One of their experiments involved an instrument called a white-Jude interferometer. This device was designed to detect extremely tiny distortions in space-time that might be produced by high-energy electromagnetic fields. The idea was simple. If space-time could be slightly distorted by controlled energy systems, even at microscopic levels, it might provide clues about whether larger distortions were theoretically possible. So far, the experiments have not detected any measurable warp effects, but the research itself remains valuable, because exploring these questions helps physicists better understand the structure of space-time. And sometimes, unexpected discoveries appear in the process. Even if warp drives remain distant dreams, the study of space-time continues to reveal fascinating insights about the universe. For instance, astronomers have discovered that space itself behaves in ways we're still trying to fully understand. Black holes, for example, warp space-time so dramatically that not even light can escape their gravity. Around black holes, time itself slows down relative to distant observers. Closer to the event horizon, time appears to stretch almost infinitely. And in the early universe, space expanded faster than light during a period called cosmic inflation. All of this suggests something extraordinary. The geometry of space-time is flexible. Under the right conditions, it can stretch, twist, and bend. Gravity itself is simply the visible effect of those distortions. So when physicists talk about warp drives, they are really talking about learning to shape space-time intentionally. It's not about breaking the laws of physics. It's about understanding them deeply enough to work with them. Of course, that understanding may take centuries, or perhaps we will discover that certain barriers simply cannot be overcome. But history has shown that scientific progress often begins with questions that sound impossible. People once believed heavier than air flight could never work, They thought radio communication across oceans was unrealistic. Even the idea of traveling to the moon seemed like fantasy for much of human history. And yet, step by step, curiosity led to discovery. For now, warp drive research remains almost entirely theoretical, but it continues to inspire new thinking about propulsion, energy, and the structure of space itself. And even if humanity never builds a warp engine, studying the idea helps us understand our universe a little better. For tonight, though, we'll leave warp bubbles and cosmic geometry drifting quietly in the background. Let those ideas settle like distant stars on a calm horizon. Because there is another curious thread in NASA's long exploration of unusual propulsion ideas, one that involves electromagnetic fields, rotating systems, and a series of experiments that some researchers hoped might reveal subtle interactions between electricity and gravity. These experiments were small, quiet, and mostly forgotten today. But for a while, they sparked an unusual amount of interest among physicists who wondered whether gravity might someday be influenced by powerful electromagnetic forces. We'll gently explore that next. For now, take another slow breath. Let your mind relax. As we continue drifting through these calm and curious corners of science, let's now turn our attention to another area that once quietly fascinated engineers and physicists. It's a subject that sits right on the edge between conventional science and speculative propulsion ideas: the relationship between electricity, magnetism, and gravity. At first glance, these forces seem completely separate. Electricity and magnetism combine into what physicists call the electromagnetic force. It governs everything from lightning storms to the circuits inside your phone. Gravity, on the other hand, feels very different. It is always attractive. It pulls objects together. And compared to electromagnetism, gravity is incredibly weak. In fact, if you hold a small magnet against your refrigerator door, and the electromagnetic force in that tiny magnet is strong enough to overcome the entire gravitational pull of the Earth on that object. That enormous difference in strength has puzzled scientists for generations. Why should gravity be so much weaker than the other forces of nature? Some physicists suspect that gravity may behave differently because it interacts with space-time itself. Others believe there may be hidden aspects of the universe that dilute gravity's strength. But during the early space age, a few engineers wondered something slightly different. What if gravity could be influenced by extremely strong electromagnetic fields? The idea wasn't completely unreasonable. After all, Einstein's equations show that energy itself contributes to gravity, and anything with energy, including electromagnetic fields, can theoretically curve space-time. In everyday situations, the effect is unimaginably small. But what if energy densities became extremely high? This question led to a handful of unusual experiments and theoretical proposals throughout the 20th century. One example involved extremely powerful rotating electromagnetic systems. Some researchers proposed that rapidly spinning magnetic fields might interact with space-time in subtle ways. If such effects existed, they would be incredibly faint, but perhaps measurable with sensitive instruments. NASA's advanced propulsion studies occasionally examined these ideas, not because they expected to discover anti-gravity engines right away, but because even tiny gravitational interactions could reveal new physics. A few experimental groups built devices designed to produce strong rotating electromagnetic fields. Large coils carried high electrical currents. Superconducting materials were sometimes used to reduce energy loss. Sensors around the apparatus measured changes in weight, acceleration, or nearby gravitational fields. Most experiments produced no unusual results. Gravity behaved exactly as expected. But the exploration itself remained interesting because it touched on deeper questions about the nature of the universe. One such question involves something called unification. For centuries, scientists have discovered that forces which appear separate are sometimes connected at deeper levels. Electricity and magnetism were once thought to be completely unrelated. But in the 19th century, physicist James Clerk Maxwell showed that they were actually two aspects of the same phenomenon. Today we call this combined force electromagnetism. Later discoveries revealed that electromagnetism and the weak nuclear force are also related. Together, they form the electroweak force. These discoveries have led physicists to wonder whether all forces might eventually be unified into a single theory, a theory of everything. In such a theory, gravity might not stand alone as a separate force. Instead, it could emerge from deeper interactions between fields, particles, and the geometry of space-time. Some theoretical frameworks, such as string theory, attempt to explore this idea. In string theory, the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. Different vibration patterns correspond to different particles. Within this framework, gravity naturally appears as a particular vibration mode associated with the hypothetical graviton. If these ideas are correct, gravity may ultimately be understood as part of a much larger cosmic symphony of vibrating energy. For now, though, these theories remain difficult to test experimentally. The energy levels required to probe such physics are far beyond anything currently achievable in laboratories. But scientists continue searching for clues in creative ways. One example involves extremely precise measurements of gravitational waves. In 2015, researchers using the LIGO observatory detected gravitational waves for the first time. These waves were produced by two black holes, merging over 1 billion light-years away. The collisions sent ripples through space-time itself. By the time those ripples reached Earth, they had stretched and squeezed space by less than the width of a proton. Yet the detectors were sensitive enough to measure them. This discovery opened an entirely new window on the universe. Instead of observing space only with light, we can now listen to the subtle vibrations of gravity itself. And these measurements may eventually reveal new insights about how gravity behaves under extreme conditions. For NASA and other space agencies, understanding gravity is more than an academic curiosity. It shapes every mission we launch. Every spacecraft trajectory must account for the gravitational influence of planets, moons, and even asteroids. Tiny variations in gravitational fields can reveal hidden structures beneath planetary surfaces. For example, NASA's Grail mission mapped the Moon's gravitational field with extraordinary precision. By measuring subtle changes in spacecraft motion, scientists discovered buried structures beneath the lunar crust, including ancient impact basins that had been hidden for billions of years. Gravity becomes a kind of invisible map, a way of seeing things that cannot be observed directly. And this ability to measure gravity so precisely continues to improve. Future missions may use even more sensitive instruments to explore gravitational anomalies across the solar system. Each measurement adds another layer of understanding, and sometimes the smallest measurements lead to the biggest discoveries. For now, though, gravity remains beautifully consistent. In every falling object, every orbiting satellite, every drifting spacecraft obeys the same quiet rules written into the geometry of space-time. Yet the curiosity that drives scientists to question those rules has never faded. Somewhere, researchers are still designing experiments, testing instruments, and watching for tiny signals that might reveal something new. Not dramatic anti-gravity engines or levitating spacecraft, but subtle clues about how the universe truly works. Because sometimes the greatest discoveries come from asking simple questions. Questions like, why does gravity behave the way it does? Why is it so weak compared to other forces? And could it someday be understood well enough to guide our journeys through space more gently than rockets do today? For now, though, let those thoughts drift quietly. Imagine the soft hum of instruments in a laboratory. Scientists watching screens filled with tiny numbers, most of them exactly as expected. But every once in a while, a small anomaly appears. And when it does, curiosity wakes up. As we continue our quiet journey through these strange and fascinating ideas, we now arrive at one of the more subtle concepts that sometimes appears in conversations about advanced propulsion. It's a concept that sounds almost poetic when you first hear it. The idea that space itself might become part of the engine. Normally, when we think about propulsion, we imagine pushing against something. Rockets push hot gas downward, and the reaction force pushes the rocket upward. Airplanes push against air with spinning propellers or jet exhaust. Even in the vacuum of space, spacecraft still rely on reaction forces. They throw mass backward in the form of exhaust, and the spacecraft moves forward. Newton's third law in action. Every action has an equal and opposite reaction. But what if a spacecraft didn't need to throw mass backward at all? What if it could interact directly with the structure of space-time itself? This idea appears in a category of theoretical propulsion, sometimes called space-time engineering. The concept is extremely speculative, but it grows naturally out of Einstein's description of gravity. If gravity is really the curvature of space-time, then motion through space might be understood as movement along the curves of that geometry. A spacecraft normally follows those curves. But what if, instead of following them, it could reshape them? The warp drive idea we talked about earlier is one example of this thinking. But there are other theoretical possibilities as well. One involves something called metric engineering. In physics, the metric describes how distances are measured within space-time. It determines how space is curved and how objects move through it. If the metric of space-time could somehow be altered locally, the paths available to objects might change as well. A spacecraft might effectively slide along newly created curves in space-time. To visualize this, imagine a sheet of fabric stretched across a table. If the fabric is perfectly flat, a marble rolled across it travels in a straight line. But if you lift one part of the fabric or stretch another, the marble's path changes. It follows the new shape of the surface. In this analogy, the marble represents the spacecraft and the fabric represents space-time. If future technology could gently reshape that fabric, even slightly, it might create new ways to move through the universe. Of course, the challenge lies in how such changes could actually be produced. So far, the only known way to curve space-time significantly is through mass or enormous energy. Planets curve space, stars curve it more strongly, black holes curve it dramatically. But the amount of energy required to create noticeable curvature on demand is far beyond current engineering capabilities. Still, physicists sometimes explore the possibility that smaller, localized distortions might be possible under certain conditions. For instance, gravitational waves demonstrate that space-time itself can ripple. These waves are created when massive objects accelerate violently, such as when two black holes collide. The waves travel outward at the speed of light, gently stretching and squeezing space as they pass, and the distortions are incredibly tiny by the time they reach Earth. But they are real, and if space-time can ripple, then in principle, it can be influenced. Some theoretical proposals imagine generating very small gravitational disturbances intentionally. Instead of using massive stars, the idea would involve carefully controlled energy systems that interact with space-time geometry. Right now, these concepts remain far beyond practical technology, but thinking about them helps physicists explore the limits of what nature might allow. Another related idea involves something called inertial manipulation. Inertia is the tendency of an object to resist changes in motion. When you push a heavy object, you feel that resistance. The greater the mass, the stronger the inertia. But inertia itself is still somewhat mysterious. Why do objects resist acceleration? One possibility, suggested by Mach's principle as we mentioned earlier, is that inertia might be connected to the gravitational influence of the entire universe. If that connection exists, it raises an intriguing possibility. Could inertia itself be influenced by altering local gravitational conditions? If a spacecraft could reduce its inertial mass, even slightly, it would require far less energy to accelerate. In theory, such a craft might perform maneuvers that would otherwise require enormous propulsion systems. Of course, these ideas remain deeply theoretical, but they continue to appear in discussions of long-term propulsion research. Because if humanity ever hopes to travel between stars, new physics may eventually play a role. Our current propulsion systems are remarkable, but they still rely on chemical energy or electric thrusters. Even nuclear propulsion concepts, which could dramatically increase spacecraft speeds, would still require long travel times to reach nearby stars. The distances between stars are simply enormous. And yet, when we look at the universe, we see natural phenomena that manipulate gravity on cosmic scales. Black holes bend light. Neutron stars create gravitational fields billions of times stronger than Earth's. And the expansion of the universe itself stretches space across unimaginable distances. Nature already performs feats that seem almost magical from a human perspective, which means the laws of physics allow far more than we can currently achieve. The challenge is understanding those laws deeply enough to harness them. For now, gravity remains a quiet guide through the cosmos. It shapes galaxies, it steers planets, it keeps stars burning and solar systems stable, and it carries spacecraft on silent journeys across billions of kilometers. Sometimes, when scientists study gravity closely, they discover subtle surprises. Other times, they confirm that the universe behaves exactly as expected. Both outcomes are valuable, because every careful measurement helps refine our understanding of the cosmos. NASA's ongoing missions continue to gather gravitational data across the solar system. Orbiters map the gravity of planets and moons. Deep space probes test our models of motion and energy, and instruments listen for the faint ripples of gravitational waves from distant cosmic events. Piece by piece, the puzzle grows clearer, and even though anti-gravity technology remains a distant dream, the search for knowledge itself continues to move us forward. For tonight, though, there is no need to solve the mysteries of the universe. Just let the ideas drift gently through your thoughts. Picture distant spacecraft gliding silently between planets, stars slowly wheeling across the night sky, and gravity, the quiet force that binds everything together, working patiently in the background of the cosmos. As we continue drifting through the quiet edges of gravity research, we arrive at a chapter that feels a little different from the others. Instead of laboratories filled with delicate instruments or theoretical physics papers filled with equations, this part of the story involves something more curious: patents. Every year, inventors around the world submit thousands of patents for new technologies. Some of them become everyday devices. Others remain theoretical designs that are never built. And occasionally, a patent appears that sounds almost unbelievable. Over the years, a number of patents have been filed describing devices that claim to interact with gravity in unusual ways. Some propose inertial reduction systems. Others describe electromagnetic propulsion methods that appear to hint at anti-gravity. Most scientists remain skeptical of these claims, but the ideas themselves are fascinating to explore. One example that received attention in recent years involved a series of patents connected to a US Navy engineer named Salvatore Pais. Pais filed patents describing several advanced propulsion concepts, including something called a high-energy electromagnetic field generator and an inertial mass reduction device. The descriptions inside these patents sounded extraordinary. They suggested that extremely powerful electromagnetic fields might interact with the quantum vacuum, the energetic background that exists even in empty space. According to the proposal, if these interactions were strong enough, they could alter the inertia of a craft, effectively reducing its resistance to acceleration. In simple terms, the vehicle might behave as though it had less mass. If such a system were ever possible, it could allow extremely rapid acceleration without requiring enormous propulsion systems. The patent documents described ring-shaped structures generating intense electromagnetic fields while rotating at high speed. These fields were proposed to interact with the vacuum energy surrounding the craft. Now, patents are interesting things. Filing a patent does not prove that a technology works. A patent simply protects the concept so that if it ever does work, the inventor holds the rights to it. Many patents describe ideas that remain theoretical or unproven. Still, the Pays patents attracted attention because they were filed through official military channels. And some accompanying documents suggested that researchers were at least curious about the underlying physics. Whether these devices could ever function as described remains an open question. Most physicists believe that the energy requirements alone would be far beyond practical engineering limits. But the patents illustrate something important about human curiosity. Engineers and scientists often explore bold ideas, even if the chances of success are very small. Sometimes those ideas fail completely. Other times, they lead to unexpected discoveries in completely different areas. History is full of examples where speculative research opened doors to real breakthroughs. The early experiments with electricity, for example, were once viewed as strange curiosities. Scientists in the 18th century played with static charges, as sparks, and spinning glass discs that generated electricity through friction. At the time, these demonstrations seemed almost like parlor tricks. Yet from those early experiments eventually came electric lighting, communication networks, and modern electronics. Curiosity often begins in small and unusual ways. Another interesting idea that has occasionally appeared in propulsion discussions is something called the EM drive. The EM drive was proposed by a British engineer named Roger Scheuer in the early 2000s. The device was described as a microwave resonant cavity, essentially a sealed metal chamber where microwaves bounce around inside. According to Scheuer's proposal, the geometry of the cavity could create a small net thrust without expelling any propellant. If true, it would violate one of the most fundamental principles of physics, conservation of momentum. For that reason, most physicists were deeply skeptical. Still, several research groups attempted to test the device experimentally. A small team at NASA's EagleWorks laboratory even built a prototype to see whether any measurable thrust could be detected. Early experiments appeared to show extremely tiny forces, but the measurements were right at the edge of instrument sensitivity. Later, more precise experiments suggested that the observed thrust was likely caused by thermal effects, experimental error, or interactions with surrounding equipment. In other words, the EM drive almost certainly does not work as originally claimed, yet the experiments themselves were valuable. They pushed scientists to develop more sensitive measurement techniques and to carefully examine the assumptions behind propulsion physics. Sometimes exploring an impossible idea still teaches us something important, and occasionally, even an idea that begins as a mistake leads to new understanding. The story of gravity research contains many moments like that. Ideas that seemed promising at first, only to be explained later by more familiar physics. But each attempt adds another piece to the larger picture. One of the most fascinating aspects of modern science is how open it remains to questioning. Even the most established theories are constantly tested. Einstein's theory of general relativity has passed every experimental challenge for more than a century. Yet physicists continue to test it with ever-increasing precision. Because if even the smallest deviation were ever discovered, it could point toward entirely new physics. That possibility keeps curiosity alive. NASA and other space agencies continue studying gravity through missions that explore the solar system and beyond. Every spacecraft trajectory becomes a new test of gravitational theory. Every planetary orbit reveals subtle details about how mass and space interact. And occasionally, new puzzles appear, small anomalies that prompt scientists to look closer. Most of the time, those puzzles eventually find ordinary explanations. But every once in a while, a deeper mystery remains. And those mysteries are what makes science so endlessly fascinating. For now, though, gravity continues to guide everything we see in the cosmos. It keeps planets circling stars. It gathers gas into glowing nebulae. It sculpts galaxies across billions of light years. And it holds us gently to the surface of our small blue world. Even though we cannot control gravity yet, simply understanding it has already allowed us to explore space in remarkable ways. Satellites orbit silently overhead. Robotic explorers travel across distant planets. And spacecraft drift through the outer solar system, guided by the quiet pull of gravity itself. The dream of anti-gravity may still be far away, but the journey toward understanding gravity continues, one careful measurement at a time. And sometimes, the quiet search for knowledge can be just as beautiful as the discoveries themselves. As we continue drifting through these quiet ideas about gravity, space, and the hidden architecture of the universe, we arrive at one of the most relaxing and thought-provoking concepts modern physics has explored. The idea that gravity might not be fundamental at all. At first, that may sound surprising. Gravity feels like one of the most obvious forces in nature. Every time you drop a spoon, every time rain falls, every time the ocean tides rise and fall, gravity is there. It feels permanent, basic, almost simple. But some physicists have begun to wonder whether gravity might actually be something deeper, something that emerges from more fundamental processes. This concept is often called emergent gravity. To understand the idea, it helps to think about something very familiar: temperature. When you touch a warm cup of tea, you experience heat. It feels like a basic property of the liquid. But temperature isn't actually fundamental. Temperature is simply a measure of how fast the tiny molecules inside the liquid are moving. If you zoom in far enough, the warmth disappears. All that exists are countless atoms bouncing and vibrating. The heat emerges from their collective motion. Some physicists believe gravity might work in a similar way. Instead of being a fundamental force like electromagnetism, gravity might arise from deeper microscopic processes within space-time itself. In other words, gravity could be the large-scale behavior of something more basic happening underneath reality. One scientist who explored this idea extensively is the Dutch physicist Erik Verlinde. Verlinde proposed that gravity might emerge from the way information is stored and organized in the universe. His work draws inspiration from another fascinating area of physics involving black holes. Black holes are strange objects. Their gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. But in the 1970s, physicist Stephen Hawking discovered something remarkable about them. Black holes appear to have temperature. They emit a faint radiation, now known as Hawking radiation. And they possess entropy, a measure of information and disorder. This discovery suggested that gravity, thermodynamics, and quantum information might all be deeply connected. Black holes seem to behave almost like thermodynamic systems, like glowing embers of pure space-time. From this insight, some physicists began to wonder if gravity itself might arise from the statistical behavior of microscopic information encoded within space. Verlinde's theory suggests that when matter moves through space, it changes the way information is distributed in the underlying fabric of the universe. Those changes produce what we perceive as gravitational attraction. In this view, gravity isn't pulling objects together directly. Instead, objects move toward regions where the universe's information structure naturally reorganizes itself. It's almost as if space is quietly adjusting its internal bookkeeping, and objects follow the resulting patterns. It's a gentle, elegant idea. And it fits with another fascinating concept sometimes called the holographic principle. The holographic principle suggests that the information describing a region of space might actually be encoded on its boundary surface. Just like a hologram on a flat plate can produce a three-dimensional image. In this picture, the universe may behave like an enormous holographic projection where space, matter, and gravity all emerge from deeper informational structures. If this idea turns out to be correct, it could completely reshape how we think about gravity. Instead of trying to manipulate gravity directly, future technologies might someday interact with the deeper informational structure that produces gravity in the first place. But for now, these ideas remain theoretical. They are beautiful mathematical frameworks, waiting for experimental confirmation, and confirming them will not be easy. And the scales involved are incredibly small. The energies required to probe such physics may be far beyond our current instruments. Still, the exploration continues, because gravity remains the one fundamental interaction that refuses to fully cooperate with quantum theory. The other forces, electromagnetism and the nuclear forces, fit comfortably into quantum physics. Gravity does not. This tension between general relativity and quantum mechanics is sometimes called the greatest unsolved problem in physics. Solving it may require entirely new ways of thinking about space, time, and reality itself. But the search is peaceful in its own way. Scientists around the world quietly explore these ideas through mathematics, computer simulations, and increasingly precise astronomical observations. Gravitational wave detectors listen for the distant echoes of colliding black holes. Space telescopes study the bending of light around galaxies. Particle physicists search for hints of deeper structures within the vacuum. Each observation brings us a little closer to understanding the true nature of gravity, and the universe continues to reveal its secrets slowly, patiently, one discovery at a time. For tonight, though, there is something calming about remembering how vast and mysterious the cosmos truly is. Gravity shapes every star you see in the night sky. It gathers clouds of gas into new suns. It holds galaxies together across unimaginable distances, and it quietly guides the motion of everything around us, from drifting satellites to falling leaves. Even though we cannot control gravity yet, simply understanding it has already allowed humanity to reach space. Every spacecraft that leaves Earth carries with it a deep understanding of gravitational motion. Engineers carefully design trajectories that weave through the solar system using gravity itself as a guide. Sometimes, spacecraft even steal tiny amounts of energy from planets through gravitational slingshots, gaining speed without using additional fuel. It's a beautiful partnership between technology and the natural laws of the universe. And perhaps one day, far in the future, deeper knowledge of gravity will allow even more gentle journeys through space. Not explosive launches, not roaring engines, but quiet movement through the geometry of space itself. For now, though, gravity remains one of the universe's most peaceful and reliable companions. Always present, always working silently in the background, and always reminding us that the cosmos is both simple and profoundly mysterious at the same time. As we continue drifting through these quiet ideas about gravity and the deeper structure of the universe, we now arrive at something that feels almost poetic: the relationship between gravity and time. Most of the time, we think of time as something steady and constant. Seconds pass, minutes follow. The clock on the wall ticks forward at a reliable pace. But according to Einstein's theory of relativity, time is not the same everywhere. Gravity changes it. The stronger the gravity, the slower time flows. This effect is called gravitational time dilation. It sounds abstract, but scientists have measured it many times with extraordinary precision. For example, atomic clocks placed on satellites orbiting Earth run slightly faster than identical clocks on the ground. The difference is very small, only fractions of a second over long periods. But it's real. Engineers even have to correct for this effect in the GPS satellites that guide navigation systems around the world. Without those corrections, GPS positions would drift by kilometers each day. Gravity bends time itself. Imagine two clocks, one sitting on the surface of Earth, the other floating far away in deep space where gravity is weaker. The clock in space will tick just a little faster, not by much, but enough for sensitive instruments to detect. Near extremely massive objects, the effect becomes dramatic. Near a neutron star or black hole, time slows down significantly relative to distant observers. Closer and closer to the event horizon of a black hole, time appears to slow almost to a standstill. From the outside, an object falling toward a black hole would seem to freeze in place, its image fading slowly as light struggles to escape the immense gravity. This strange connection between gravity and time leads to fascinating questions. If gravity affects time, and time is part of space-time itself, then manipulating gravity might also influence the flow of time. Of course, this doesn't mean time machines are hiding in secret laboratories, but it does remind us that gravity is far more than just a downward pull. It is part of the geometry of reality itself. In fact, modern physics describes gravity not as a force in the traditional sense, but as the shape of space-time. Mass and energy tell space-time how to curve, and that curvature tells objects how to move. Planets follow the curves created by stars. Moons follow the curves created by planets, and everything else follows the gentle slopes of space-time around them. It's a beautiful idea. Instead of invisible forces pulling things around, the universe simply has shape, and objects naturally follow that shape. When we imagine future technologies that might interact with gravity, we're really imagining ways to interact with this geometry. Perhaps someday, scientists will discover methods to create tiny distortions in space-time intentionally, not large enough to bend planets or stars, but maybe just enough to influence motion in subtle ways. For now, though, the curvature of space-time remains governed by enormous energies and massive objects: planets, stars, black holes. Yet our understanding of these phenomena continues to grow. One of the most exciting developments in recent years has been the direct observation of gravitational waves. These waves were first predicted by Einstein in 1916, but detecting them required technology far beyond what existed at the time. It wasn't until 2015 that scientists using the LIGO observatory finally confirmed their existence. Two black holes had collided more than 1 billion light-years away. The collision released enormous energy, sending ripples through space-time itself. Those ripples traveled across the universe at the speed of light, and when they reached Earth, they stretched and squeezed space by incredibly tiny amounts. The change in distance was smaller than the width of a proton, yet the detectors were sensitive enough to measure it. For the first time in history, humanity had directly observed the vibration of space-time itself. Since then, many more gravitational wave events have been detected. Black holes merging, neutron stars colliding, each event sending subtle waves across the cosmos. These observations are opening an entirely new way of studying the universe. Instead of observing only light, we are now listening to the quiet rhythm of gravity itself. And who knows what future discoveries might come from this new window on reality. Perhaps gravitational waves will reveal unknown types of cosmic objects. Perhaps they will help physicists test the limits of Einstein's theory under extreme conditions. Or perhaps they will hint at deeper layers of physics still waiting to be understood. For now, though, these discoveries remind us of something calming. The universe is alive with motion. Space-time itself vibrates with events happening across unimaginable distances. Black holes dance around each other in silent spirals. Stars collapse and merge. Galaxies slowly drift through the cosmic web. And all of it is guided by the quiet influence of gravity. A force so gentle we barely notice it, yet powerful enough to shape the entire cosmos. As we rest here tonight, thinking about these ideas, it's comforting to remember that gravity is always working quietly in the background, holding our planet together, guiding the moon through its orbit, keeping the oceans gently moving with the tides, and carrying spacecraft through the solar system on silent trajectories. The dream of controlling gravity may still lie far in the future, but the simple act of understanding it already connects us to the deeper workings of the universe, and that understanding continues to grow, slowly, patiently, one discovery at a time. As we continue drifting deeper into this quiet exploration of gravity and the hidden forces shaping the universe, we now arrive at one of the most mysterious subjects in all of modern science. Something that scientists believe makes up most of the universe, yet cannot be seen directly. This mysterious substance is known as dark matter. For a long time, astronomers assumed that the stars, planets, and glowing clouds we see through telescopes represented most of the matter in the cosmos. Galaxies appeared to be enormous islands of stars, held together by gravity in a slow cosmic dance. But in the early 20th century, careful measurements began to reveal something strange. Galaxies were spinning faster than expected, much faster. According to the visible mass within them, many galaxies should have been unable to hold themselves together. The stars at the outer edges were moving so quickly that they should have escaped the galaxy's gravity and drifted away into space. But they didn't. Instead, the galaxies remained intact. The only explanation that made sense was that there must be far more mass present than telescopes could see. Invisible mass. This hidden mass became known as dark matter. It doesn't emit light. It doesn't reflect light. And it doesn't appear to interact with ordinary matter except through gravity. Yet its gravitational influence is enormous. When scientists study the motion of galaxies, the bending of light across cosmic distances, and the structure of the universe itself, they find that dark matter appears to make up about 85% of all matter in the cosmos. Ordinary matter, the atoms that form stars, planets, oceans, and people, makes up only a small fraction. This discovery changed our understanding of gravity on the largest scales. If dark matter exists everywhere around galaxies, then gravity may be operating within structures we cannot see. Imagine a galaxy not just as a spinning disk of stars, but as a glowing island embedded inside a vast, invisible halo of dark matter. That halo extends far beyond the visible edges of the galaxy. It quietly shapes how stars move and how galaxies interact with each other. NASA missions and telescopes have spent decades studying these effects. One of the most fascinating techniques used by astronomers involves something called gravitational lensing. When light from a distant galaxy passes near a massive object, like another galaxy cluster, the gravity of that cluster bends the light slightly. It acts like a cosmic lens. By measuring how the light bends, scientists can estimate how much mass must be present. And often, the visible matter accounts for only a small portion of the required mass. The rest must be dark matter. Even though we cannot see dark matter directly, its gravitational influence leaves fingerprints everywhere in the structure of the universe. Entire clusters of galaxies appear to be held together by it. The cosmic web, the enormous network of galaxies stretching across billions of light years, seems to follow patterns shaped by dark matter halos. Yet despite decades of research, we still don't know exactly what dark matter is made of. Some scientists believe it consists of unknown particles that rarely interact with normal matter. These hypothetical particles are often called WIMPs, or weakly interacting massive particles. Others have proposed lighter particles known as axions. Large experiments deep underground are searching for signs of these particles. Massive detectors sit in dark, quiet chambers beneath mountains, shielded from cosmic radiation. Scientists wait patiently, hoping that one day a dark matter particle might collide with an atom inside the detector. If it does, the signal would be incredibly faint, but it could reveal the nature of the invisible mass shaping our universe. Another possibility is that our understanding of gravity itself might need to be adjusted. Some physicists have proposed theories where gravity behaves slightly differently at extremely large distances. One example is something called modified Newtonian dynamics, or MOND. In this framework, gravity becomes stronger than expected at very low accelerations, which could explain galaxy rotation without requiring dark matter. Most astronomers still favor the dark matter explanation because it fits many observations more consistently. But the debate itself highlights something important. Gravity, even after centuries of study, may still hold surprises. If dark matter particles are eventually discovered, they could reshape our understanding of the cosmos. And if gravity behaves differently on cosmic scales, it could reveal entirely new aspects of space-time physics. Either way, the mystery continues. NASA's telescopes, along with observatories around the world, continue mapping the distribution of dark matter across the universe. Projects like the James Webb Space Telescope and large sky surveys are revealing new details about how galaxies formed and evolved. By studying the motion of stars, the bending of light, and the structure of galaxy clusters, scientists are gradually building a clearer picture of the invisible scaffolding that supports the universe. It's an extraordinary idea to think about. Most of the universe may be made of something we cannot see, and gravity, the quiet force that guides everything, is our main tool for detecting it. The same force that pulls apples from trees is also helping us uncover the hidden mass of galaxies billions of light years away. For now, dark matter remains one of the great mysteries of modern science. But mysteries are often where the most exciting discoveries begin. As scientists continue exploring gravity, space-time, and the hidden structure of the cosmos, new ideas will undoubtedly emerge. Some will turn out to be wrong. Others may open doors we never expected. And somewhere within those quiet experiments and distant observations, the universe may slowly reveal its deeper secrets. For tonight, though, it's enough simply to imagine the vastness of the cosmos. Galaxies turning slowly in the darkness, invisible halos of matter shaping their motion, and gravity, silent, patient, and everywhere, guiding the dance of the universe. As we continue drifting through the calm mysteries of gravity and the universe, let's now turn to a thought that has quietly crossed the minds of many scientists, philosophers, and curious observers of the cosmos. The idea that somewhere, far out among the billions of galaxies, there may exist civilizations far older and more advanced than our own. And if such civilizations exist, one of the most fascinating questions we can ask is this: what might their understanding of gravity look like? Humanity has only been studying gravity scientifically for a few centuries. From Newton's discovery that gravity pulls objects together, to Einstein's realization that gravity is really the curvature of space-time, our knowledge has grown rapidly, but it is still very young. In cosmic terms, our scientific understanding is just beginning. Imagine a civilization that has been exploring physics not for a few hundred years, but for tens of thousands, or even millions of years. Their understanding of gravity could be vastly deeper than ours. They might know how to manipulate the geometry of space-time in ways that feel completely impossible to us today. Perhaps they could generate controlled gravitational fields. Perhaps they could shape space itself, guiding spacecraft across vast distances without rockets or fuel. Perhaps they could travel between stars quietly, gliding along engineered curves in space-time. These ideas may sound like science fiction, but they arise naturally when scientists think about the long-term future of physics. One way researchers sometimes discuss advanced civilizations is through something called the Kardashev scale. The Kardashev scale was proposed by the Soviet astrophysicist Nikolai Kardashev, in 1964. It describes civilizations based on how much energy they are able to harness. A Type 1 civilization can use all the energy available on its home planet. Humanity is not quite there yet, though we are slowly moving in that direction. A Type 2 civilization would be able to harness the energy of an entire star. Some scientists imagine such a civilization building enormous structures around a star, sometimes called Dyson spheres, to capture much of its energy output. A Type 3 civilization would be able to control energy on the scale of an entire galaxy. At those levels of energy and technological sophistication, it's possible that gravity manipulation could become achievable. After all, we already know that energy and gravity are connected through Einstein's equations. Mass and energy both curve space-time. If a civilization could control enormous amounts of energy, it might be able to shape that curvature intentionally. Instead of launching rockets, they might create gravitational pathways. Instead of burning fuel, they might glide through carefully engineered distortions of space-time. Even today, human engineers already make small use of gravity in clever ways. We send spacecraft on long journeys that weave around planets, borrowing momentum through gravitational slingshots. The Voyager probes, for example, used a rare alignment of outer planets to gain enormous speed without additional fuel. By swinging past Jupiter and Saturn in precise trajectories, they accelerated dramatically, eventually escaping the solar system entirely. Gravity became part of the engine. Future technologies may expand on this idea. Some researchers have imagined spacecraft that use solar sails, which harness the gentle pressure of sunlight to move through space. Others have proposed laser sails, where powerful beams of light push tiny spacecraft to tremendous speeds. These technologies are far more achievable than anti-gravity, and they may allow humanity to reach nearby stars within the next century or two. But even these methods still rely on familiar physics. True gravity manipulation, shaping space-time directly, remains a far more distant possibility. Yet the idea continues to inspire both scientists and dreamers. Because if gravity could someday be controlled, it would transform our relationship with the universe. Space travel would become quieter, more graceful. Instead of explosive launches and roaring engines, spacecraft might simply rise gently from planetary surfaces. They might drift through space with barely any visible propulsion. Journeys that currently take years might become far shorter, and distant star systems might eventually become reachable destinations rather than distant points of light. Of course, these ideas remain deeply speculative. The laws of physics may ultimately place limits that we cannot overcome, but exploring those possibilities is part of what drives scientific curiosity forward. Every generation asks new questions. Every discovery opens new doors. And sometimes the most extraordinary ideas begin with simple observations. Are an apple falling from a tree? A strange shift in the orbit of a planet? A faint ripple in the fabric of space-time detected by instruments on Earth? Gravity has guided countless discoveries throughout human history, and it continues to guide our exploration of the cosmos today. Even though we cannot control gravity yet, we are learning more about it with every passing year. New telescopes, new space missions, new experiments probing the deepest structure of reality. Each one adds another small piece to the puzzle, and perhaps one day, long in the future, humanity, or some other civilization somewhere in the vast universe, will learn to shape gravity itself. For now, though, gravity remains the quiet architect of the cosmos. It holds stars together. It guides planets through their orbits, and it gently anchors us to the surface of our small blue world. As we sit here tonight, thinking about these ideas, it's comforting to imagine the vastness of the universe unfolding slowly around us. Billions of galaxies drifting through space, invisible halos of dark matter guiding their motion. black holes warping space-time in silent spirals, and gravity, always present, always working quietly behind the scenes. As we begin the final stretch of tonight's journey, let's slow things down even more and take a quiet step back from all the theories, experiments, and possibilities we've explored. Because when you look at gravity from a distance, beyond the equations and the research labs, it starts to feel less like a mystery to solve and more like a gentle rhythm woven through the universe. Gravity is the reason stars exist. Long before Earth formed, vast clouds of hydrogen drifted through space. Over time, tiny irregularities allowed gravity to gather that gas together. Slowly, patiently, the clouds collapsed inward until the pressure at their centers ignited nuclear fusion. A star was born. Without gravity, those clouds would have remained thin and scattered. No stars, no sunlight, no planets forming in warm disks of dust. Gravity built the stage for everything that followed. Planets formed when gravity gathered tiny grains of dust into larger and larger clumps. Over millions of years, those clumps became rocks, then worlds, then entire planetary systems circling their parent stars. Even galaxies themselves formed this way. Across the early universe, gravity slowly drew matter into enormous structures. Billions of stars gathered into spiraling islands of light that we now call galaxies. Each galaxy drifting through the cosmos like a luminous whirlpool, and all of it guided by the same quiet force. Gravity never rushes. It works slowly, often over millions or billions of years. Yet given enough time, it shapes the entire architecture of the universe. It bends light around distant galaxies. It traps time itself near black holes. It guides the slow orbit of moons and planets in elegant celestial patterns. And right here on Earth, it keeps everything gently connected to the ground beneath us. When astronauts leave Earth and enter orbit, they experience something unusual. It feels like gravity has disappeared. But in reality, gravity is still there. The spacecraft and the astronauts are simply falling together around the Earth in a continuous curve. They are caught in a delicate balance between motion and gravity, forever falling but never quite reaching the ground. That graceful motion is what keeps satellites circling above us. Communication satellites, weather satellites, navigation satellites guiding travelers across oceans and continents, all of them moving in silent arcs around the planet, guided by the same invisible force that drops a leaf from a tree. Gravity connects the everyday world with the deepest reaches of the cosmos. It links the motion of your coffee cup sliding across a table with the orbit of Jupiter around the Sun. The same equations describe both, and perhaps that's what makes gravity so calming to think about. It is universal, simple in appearance, yet endlessly profound in its consequences. Even when we imagine future technologies that might someday interact with gravity in new ways, warp drives, gravitational propulsion, engineered space-time, those ideas still begin with the same quiet understanding. Gravity is not an enemy to defeat. It is part of the universe's design, and the more we learn about it, the more we realize how beautifully consistent it truly is. NASA's exploration of gravity has already taken humanity far beyond what earlier generations could imagine. Robotic spacecraft now wander across the surfaces of Mars. Probes orbit distant planets like Jupiter and Saturn, studying their moons and hidden oceans. The Voyager spacecraft continue their silent journey into interstellar space, guided only by the momentum of their launch and the gravitational paths that carried them outward decades ago. They drift through the darkness between stars, still carrying faint signals from Earth, messages from a tiny planet that learned to understand gravity well enough to send explorers across the solar system. And that understanding continues to grow. Each new discovery adds another piece to the puzzle. Each observation reveals another subtle detail about how gravity shapes the universe. Perhaps one day, far in the future, humanity will learn to manipulate gravity in ways we cannot yet imagine. Or perhaps gravity will remain the quiet background force that guides our journeys rather than powering them directly. Either way, the universe will continue its slow and patient dance. Stars will be born. Galaxies will turn. Black holes will merge and send ripples through space-time. And gravity will quietly hold everything together. For now, though, there's nothing left to figure out tonight. You've wandered through distant galaxies, theoretical propulsion ideas, strange experiments, and the deepest questions physicists continue to explore. Now it's time to simply let those ideas settle, like starlight slowly fading into the horizon. As we continue drifting gently through these ideas, we're beginning to reach the later part of our quiet journey. Tonight, we've wandered through many fascinating corners of gravity research, from early NASA propulsion studies to deep questions about the structure of space-time itself. And one thing becomes very clear when you step back and look at the bigger picture. Gravity is both incredibly familiar and incredibly mysterious. It's the force that feels the most ordinary in our daily lives. It keeps our feet on the ground. It pulls rain from the clouds. It guides the oceans as the moon quietly lifts and lowers the tides. Yet at the same time, gravity is also one of the deepest puzzles in all of physics. We know how gravity behaves. We can calculate it with extraordinary precision. Spacecraft travel billions of kilometers through the solar system using gravitational equations that work almost perfectly. But we still don't fully understand why gravity exists in the form that it does. Einstein showed that gravity emerges from the curvature of space-time. Massive objects bend the geometry of the universe, and other objects move along those curved paths. It's a beautiful explanation, and one that has passed every experimental test for over a century. But beneath that elegant theory lies an even deeper mystery. How does gravity connect to the quantum world? Quantum mechanics describes the behavior of particles at the smallest scales. Electrons, photons, and atoms follow rules that often feel strange and counterintuitive. Particles can exist in multiple states at once. They can become entangled across large distances, and probabilities replace certainty at the microscopic level. Yet gravity does not easily fit into that picture. When physicists try to combine general relativity and quantum mechanics into a single unified theory, the equations become extremely difficult to reconcile. It's as if two powerful descriptions of nature are both correct, but incomplete. Somewhere deeper beneath them may lie a more fundamental framework that explains both gravity and quantum behavior together. Physicists have spent decades searching for this deeper theory. Ideas like string theory, loop quantum gravity, and emergent space-time all attempt to bridge the gap between these two pillars of modern physics. And although none of these theories have been fully confirmed yet, they offer fascinating glimpses into what the deeper structure of reality might look like. One possibility is that space-time itself may not be smooth and continuous at the smallest scales. Instead, it could be made of tiny, discrete units, almost like a fabric woven from incredibly small threads. At those scales, gravity might emerge from the way those threads connect and interact. Another possibility is that gravity arises from quantum information stored throughout the universe. In that picture, the geometry of space-time may actually reflect deeper patterns of information processing happening beneath the surface of reality. These ideas may sound abstract, but they show how far scientists are willing to explore in their search for understanding. One, because every great discovery in physics began with someone asking questions that seemed impossible at first. When Newton first described gravity mathematically, many people wondered how a force could act across empty space. When Einstein proposed that space and time themselves were flexible, the idea seemed almost unbelievable. And yet, both theories turned out to describe the universe with remarkable accuracy. The future of gravity research may bring equally surprising insights. NASA continues to explore gravity through space missions that map planetary fields, study black holes, and observe the distant structure of the universe. Telescopes observe how gravity bends light around massive galaxies. Gravitational wave detectors listen for the quiet echoes of cosmic collisions. And physicists continue searching for subtle hints of new phenomena hidden within the fabric of space-time. Every discovery brings us one step closer to understanding gravity not just as a force, but as a fundamental feature of the universe itself. For now, though, the idea of anti-gravity remains mostly a dream. A fascinating one, but still far beyond our current technology. Yet dreaming about such possibilities has always been part of scientific progress. Curiosity pushes us forward, and sometimes the questions themselves are just as valuable as the answers. Tonight we've explored NASA's curiosity about gravity, theoretical propulsion concepts, strange laboratory experiments, and the deeper mysteries of the cosmos. But the most calming realization might be this. Even though gravity still holds secrets, it is also one of the most reliable forces in the universe. It quietly guides the motion of planets, it shapes galaxies across billions of light years, and it gently anchors us to the surface of our world as we rest here tonight. Every star you see in the night sky is held together by gravity. Every galaxy slowly turning in the darkness follows its invisible pull. Gravity connects everything in the cosmos, from the smallest grains of dust to the largest clusters of galaxies. And that quiet connection stretches across the entire universe. As we reach the end of tonight's quiet journey, there's no need to rush anywhere. The universe we've been wandering through doesn't hurry, and neither do we. So let's take a final moment to drift peacefully among the ideas we explored together. Tonight we followed gravity from the familiar ground beneath our feet, all the way out into the deepest reaches of space. We looked at the questions scientists ask when they study one of the most gentle yet powerful forces in existence. We wandered through NASA research, strange laboratory experiments, theoretical propulsion ideas, and the hidden structure of the cosmos itself. And in the process, something simple becomes clear. Gravity is both ordinary and extraordinary at the same time. It is the quiet force that drops a leaf from a tree, yet it also bends light around distant galaxies. It keeps the moon circling Earth, yet it can slow time itself near a black hole. It shapes the paths of spacecraft drifting through the solar system, yet it also builds the enormous cosmic web that stretches across billions of light years. For centuries, humanity has slowly learned how to read the language of gravity. Newton showed us that gravity connects the falling apple with the orbit of the moon. Einstein revealed that gravity is really the curvature of space and time themselves. Modern observatories now listen to the faint echoes of gravitational waves from distant cosmic collisions. Each generation adds a new chapter to the story, and yet, even after all this progress, gravity still keeps some of its secrets. We don't fully understand how gravity fits into the quantum world. We don't know exactly what dark matter is made of. We are still learning how space-time behaves under the most extreme conditions the universe can create. But that's part of what makes the cosmos so endlessly fascinating. The universe is not a finished book. It's an unfolding story. Every telescope pointed toward the sky, every spacecraft sent beyond Earth, and every quiet physics experiment adds a few more pages. And somewhere, perhaps many years from now, new discoveries may deepen our understanding of gravity even further. Maybe scientists will uncover new connections between space, energy, and information. Maybe new propulsion methods will emerge that allow spacecraft to move more gracefully through the cosmos. Or perhaps gravity will remain exactly what it appears to be, a beautifully consistent force guiding the motion of everything around us. Either way, the quiet elegance of gravity will continue shaping the universe long after we fall asleep tonight. As you rest, imagine the vast calm of space stretching in every direction. Galaxies slowly turning in the darkness. Stars burning quietly across the sky. Invisible halos of matter guiding their motion. And gravity, the gentle architect of the cosmos, patiently holding everything together. Even now, thousands of satellites drift silently around Earth, following invisible paths through space-time. Far beyond them, spacecraft continue their long journeys through the solar system. And even farther away, the Voyager probes glide through the quiet darkness between stars, still carrying faint whispers from our small blue planet, all of them moving through the universe according to the same elegant laws we explored tonight. For now, though, you don't need to hold on to any of these ideas. Let them fade softly into the background, like distant stars disappearing at dawn. Let your shoulders relax. Let your breathing grow slower and deeper. And let the quiet rhythm of gravity, the same force guiding planets and galaxies, gently guide you toward rest. If you enjoyed tonight's journey with Sleepy Tin Foil Hat, feel free to subscribe and leave a comment telling me where in the world you're listening from tonight. I always enjoy seeing how far these quiet explorations travel across the planet. And if you're still awake, there will be another relaxing mystery waiting for you in the next video. But if sleep is already beginning to pull you in, then simply close your eyes and drift with it. Thank you for spending this peaceful time exploring the universe together. Sleep well, and good night.